Hi, welcome to Lecture 13b of Differential Equations in Linear Algebra. I want you to go watch Lecture 13a first before you watch this if you are new to this video. It was about differential equations, but we were making our first real deep connections to linear algebra as we've been talking about in our B lectures. So I would encourage you to watch that first. Lecture 13b, we're going to spend a fair amount of time reviewing. I think we need to talk about linear transformations, kernels, images, and how it's related to matrix multiplication and matrix inversion. List out some facts that I've mentioned verbally and illustrate it with examples just to get it clear in our minds. And then the other thing we're going to do is introduce the idea of the determinant of a square matrix. I'll give you the formulas in the 2x2 and 3x3 case, and I'll talk about some properties, but I'm not going to do general calculations for determinants of 4x4, 5x5, or 6x6 matrices because it just gets to be too much of a pain. But determinants are pretty interesting, so it's definitely worth getting into to some degree. All right, so let's jump ahead to the linear algebra content. Review. What have we learned? Okay, a lot of important things to get across here. What have we learned about linear transformations, matrices, composition of linear transformations, matrix multiplication, and inversion, both of linear transformations and of matrices? All right, recall, suppose we've got a linear transformation, T, going from Rn to Rm. So this is going from n-dimensional space to m-dimensional space. I can think of elements of n-dimensional space either as n-dimensional points, n tuples of numbers, or more commonly for us as n-dimensional vectors, column vectors. We write the components, there would be n of them. That is the domain of this function. Here's the codomain, is m-dimensional space. N and m are positive integers, they do not have to be the same. Linear transformations are functions, and we call them linear transformations because they are linear. And what does that mean? That means operation preserving, which means this is true. T of alpha u plus beta v, T of this linear combination, is the corresponding linear combination with the same weights, alpha and beta, of the output of t at u and the output of t at v. Why is this called operation preserving? Well, in reality, the plus signs on both sides, and in fact even the scalar multiplications, mean different things, technically speaking, if n and m are different. Here you're adding two, well, you're multiplying scalars alpha and beta times two n-dimensional vectors, u and v, and adding then ultimately two n-dimensional vectors. But the plus sign here in the scalar multiplication there means something different if m is different than n. You've got m-dimensional vectors over here, alpha times an m-dimensional vector, beta times an m-dimensional vector, and you're adding two m-dimensional vectors. So technically speaking, the plus signs and the scalar multiplications mean different things here. But those operations are being preserved by this function. That's why it's called operation preserving. As I introduced in lecture 13a, this upside down A means for all. It's called the universal quantifier. You see it here and here. Nice, convenient shorthand for all scalars A and B in the real number system and for all vectors U and V in n-dimensional space. Such a linear transformation, as we've talked about, has a matrix. And the order of the n and m gets switched. The domain is n-dimensional space, the codomain is m-dimensional space. That means its matrix has to be m by n, m rows and n columns. Because we're going to multiply it by an n-dimensional vector to get an m-dimensional vector. That's why. Usually for T I've called this matrix A, but I'm purposely calling it B here because, as with the composition lecture where we talked about another linear transformation, S, it's going to have a matrix A, and it's kind of alphabetical order idea. S comes before T and A comes before B. Though I think there's one spot here where the alphabetical order gets messed up in a certain way. Don't worry about it. This is sometimes called the matrix of a linear transformation. LT means linear transformation. It does not mean Lawrence-Taylor. That's a reference for 40 and 50-year-olds like me. You can look it up, Lawrence-Taylor. Call them LT. Actually, also there's Ladany and Tomlinson too, is LT. That's a bit more recent. That defines its formula via matrix vector multiplication. T of x equals b times x. I always say that in your mind. t of x, this is an input for a function, t is a function, equals b times x, that's a matrix times a vector. The output is in m-dimensional space, because the codomain of t is m-dimensional space. The input is n-dimensional space. In fact, as I verbally described, in the 2x2 case, in lecture 12b, there is a way to quickly figure out the columns of the matrix. I did it in the 2x2 case. I said that if you know what t of I hat is, and you know what t of j hat is, put those in the columns of the matrix, and that will be the matrix for the linear transformation, where I hat is 1, 0, and j hat is 0, 1. Our standard unit vectors, length 1, in the horizontal and vertical directions. I'm essentially saying the same thing here, but with different notation. EI, this is not the number E. EI is often the notation used for what's called the ith standard basis vector, with a 1 in the ith spot and zeros elsewhere. I hat could also be called E1. And I made the E boldface, so I'll put a little arrow above it. J hat could also be called E2. You don't put arrows above the I hat and the j hat because their hat kind of serves as their decorations. These things are things they wear, so to speak. EI in general in n-dimensional space, you'd have a bunch of zeros and then a 1 and then a bunch of zeros. This 1 would be in the ith position, ith component. You know, if the space were 100 dimensional and I were 17, this would be in the 17th spot. You'd have 16 zeros before it. And 17th spot would be a 1, and how many would be after it? 83 after it, I guess. Would be all zeros. The ith column of B is EI's image under T. You could write this. Here's B. Here's our notation for a matrix where these vectors are the columns. There's n of them. Right? B is m by n. I'm saying B1 is T of E1, B2 is T of E2, B3 would be T of E3, etc. Bn would be T of En. That's a quick way to figure out the columns, and it is worth knowing even now. I'm not fully explaining this. Maybe you want to figure it out. Why? Why does this work? With this notation, we can also write T of x equals B times x equals this times x equals this times x. But then, hey, by the definition of a matrix times a vector, I do a linear combination of those columns with the components of the vector as the weights. The components of boldface x are unboldface x1, x2, x3, etc., through xn. There's your linear combination of the columns of the matrix. It's worth knowing and thinking about. This is a handy kind of thing to realize. It also turns out that, as I've mentioned verbally, the kernel of T is the zero vector if and only if T is 1 to 1. Oh, and I should have called it null space of B there instead of null space of A. I did mention the null space before. It's the same idea. The kernel of T is the set of everything that gets mapped to the zero vector. That's the same as the null space of the matrix, the set of every x such that B of x is 0. B times x, excuse me, B times x. Why null with one L? Just because it matches 3 letters there, and you could put 2 L's, but null space. I have mentioned this is equivalent to T being 1 to 1. Okay? I haven't proved that, but that is true. We will probably prove it sometime in the next few lectures. And the image of T is all of the codomain Rm if and only if T is onto. That's the definition of onto, actually. There's nothing to prove there. Set of all outputs of T equals Rm if and only if T is onto. That's just by definition of what onto means. So there's nothing to prove there. This is also called the column space of B. Okay? The column space, by definition, is the matrix is the set of all linear combinations of the columns. That's the definition of the column space. I did mention that before, briefly. Mentioning it here again. I will probably write it down in some future lectures. The column space of a matrix is the set of all linear combinations of its columns. And because of the relationship between T of x equals B times x equals linear combinations, the image of T is the same as the column space of B. Think about that. Continuing to review, if we've got another linear transformation from Rm to Rp, we're going to want to compose S and T, but we can only do it one way in this case. S composed T goes from Rn to Rp. T goes from Rn to Rm. S goes from Rm to Rp. The composition, do T first, then S, notated by this symbolism, goes from Rn to Rp. This means do T first, then S. Work from right to left. It's also going to be a linear transformation, so it's also going to have a matrix. And that matrix is found by matrix multiplication. So I'm saying A is now the matrix for S. B was the matrix for T. B was M by N. A is P by M. A here is P by M. B was M by N. The inner numbers match. They're both M's, so we can multiply. And the answer is going to be P by N. Look at the outer numbers. P by N. Certainly you can see you've got N columns there. There's going to be P rows because A times a vector is P dimensional. The matrix product is defined this way. So you got these two matrices, capital A and capital B. Boldface B1, B2 through Bn are the columns of capital B. There are n of them. You can make this new matrix that's got n columns as well. Those columns are these vectors, AB1, AB2 through ABn. Those are p-dimensional vectors. This matrix is P by n. There's a couple lectures ago, I think, that I explained why this was a good idea. And to finish, you'd need to do these calculations for these columns, or, as I mentioned, I think in lecture 12b, you can think about it in terms of dot products. I'm not talking about the dot products in this lecture, but you can compute A times B in practice. It's quicker to do it using dot products of rows of the matrix on the left with columns of the matrix on the right. Okay? We will come back to using that. I'm just not talking about it now. If T goes from Rn to Rn, note the domain and codomain are the same here. So its matrix is going to be square, same number of rows as columns, n rows, n columns, n by n matrix. For linear transformation to be one-to-one and onto, the dimensions have to be the same it turns out. In this case. If it is both one-to-one injective and onto surjective, then it is called a one-to-one correspondence. One-to-one correspondence, also called bijective. Any bijective function between any two sets, don't have to be Rn or something, could just be arbitrary sets, automatically has an inverse function. So in this case, T would have an inverse function, an inverse linear transformation, with the same domain and codomain. In the general case, the function and its inverse don't have to have the same domain and codomain. But with these kind of things, linear transformations in this way, they do. It's got the following properties under composition with T, which we talked about in 12b. T composed T inverse equals T inverse composed T equals the identity function on Rn. I'm not showing the inputs. I could have. I could have emphasized this is T of T inverse of x equals T inverse of T of x equals x for all x in Rn. And the identity function on Rn just maps every vector to itself. It's actually a linear transformation. This is the same as the identity matrix times x. The matrix of the identity function is the identity matrix. In has ones along the main diagonal, those are a bunch of ones, and zeros elsewhere. It has the property that if you multiply it times any n-dimensional vector, you get that vector back. In times x equals x for all x in Rn. But here I'm running the same fact without bothering with the inputs. Emphasizing the composition operator, the circle operator, it's a binary operator. It takes two things and gives you something new. In this case, two functions and gives you a new function. In general, it's not commutative, but with inverse functions, it is. At least when the node domain and codomain are the same in both cases for T and T inverse. Hang with me here. If in the case where T is invertible, it's got an inverse function. Its n by n square matrix, same number of rows as columns, A, is also invertible, as we talked about in 12b. There's an n by n matrix, call it A inverse, with the property that A times A inverse equals A inverse times A equals the n by n identity matrix. And as I just mentioned, In times x equals x for all x in Rn. Definitely with the T inverse, you do not want to think of it as -1 power. These undo each other with respect to composition, not multiplication. But with the matrices, in a way, it's kind of a -1 power because you're dealing with multiplication. However, I did put a note in lecture 12b that you don't want to write 1 over A, because in that kind of, you only write that kind of thing when you're dealing with situations where multiplication is commutative, and in general, A times B does not equal B times A, even if you can do both multiplications. We can find A inverse or verify it doesn't exist by row reduction. This is the basic idea. I'm not showing details. You make an augmented matrix. If A is n by n, again, this matrix is going to be n by 2n. It's made up of two n by n parts. The A is n by n, the I is meant to be In. It's n by n. If, after reduction to reduced row echelon form, it looks like this, meaning the first n by n piece is In, which would mean, for example, you would not have a row of zeros, or two rows of zeros, then whatever's here will be A inverse. If you get a row of zeros, or a row of zeros even in this first part on the left, even if it's non-zero over there, that will mean A is not invertible. A inverse will not exist, and that means T itself is not invertible, which also means it won't be onto and it won't be 1-to-1. When T in this situation is onto and 1-to-1, it will be invertible. A will be invertible as well. Okay, and vice versa. If A is invertible, this will be 1-to-1 and onto it will be invertible. All right, I'm going to end with introduction to determinants. Is there another way to determine whether a square matrix is invertible or not? Pun intended. Determinant. It's not the only reason to call it a determinant. Probably not, but It is a determining thing for a lot of situations. Let's consider the 2 by 2 case first. T goes from R2 to itself. It's got an associated matrix that is 2 by 2. I went back to calling it A here instead of B. Is there a simple condition on the values of the numbers, little a, little b, little c, little d, that will guarantee invertibility of both A and T? Yes, there is. How do you find it? Do some row operations on a general augmented matrix and see what happens. I'm going to assume we never divide by 0. I'm just not going to worry about that initially, but then we will think about it at the end. What do I mean by a general augmented matrix? I mean this kind of thing. A, B, C, D, that's your coefficient matrix. That's your capital A. The last column I'm calling U and V. Essentially, I'm trying to solve an arbitrary system of equations here involving these numbers. AX plus BY equals U and CX plus DY equals V. I'm wondering, that's an A, that's a C. I'm wondering, are the conditions on A, B, C, and D such that I can solve for X and Y in terms of U and V? Conditions under which this linear transformation would be ondeterminant. Do row operations in this general setting. First, put a 1 in the upper left corner there, a leading 1 in the first row. In other words, multiply row 1 by 1 over A, assuming A is not 0. That becomes a 1, this becomes a B over A, this becomes a U over A, assuming A is not 0. Then we want to get a 0 under it. So we need to multiply row 1 by negative C and add it to row 2 and put the answer in row 2 to get a 0 there. Let's continue with our dashed lines here. There's a 0 there. What about there? Negative C times B over A plus D is D minus BC over A. And negative C times U over A plus V is V minus CU over A. All right? This step right there is actually not a row operation. It's just an equal sign. That's not a typo. I'm just getting a common denominator here and here of A. So I got to multiply D by A over A. And that's why I get the A times D there. You see the A down there. Here I got to multiply V by A over A, so I get an A over V, A times V there. Next step is to make this a 1, a leading 1 in the second row. I guess I should multiply it by A divided by AD minus BC to, in other words, multiply by its reciprocal to make it a 1. And if I do that to this term, I got to do it to this one as well. Multiply that fraction by A over AD minus BC. The A's will cancel, leaving you with this. Right there. Let's stop there. I mean, I didn't go all the way to reduce row echelon form. I'd want to do one more thing. I'd want to multiply row 2 by negative B over A and add it to row 1 to make this a 0 there. But let's stop there. As long as we haven't divided by 0 anywhere, we can stop here to see that the general system, this thing here, it would actually be consistent. There would be a solution as long as we're not dividing by 0. Because this would say, y is this number as long as we're not dividing by 0. And if y is that number, you could substitute and find x as well. Evidently, this is going to work as long as we're not dividing by 0, meaning A is not 0 and AD minus BC is not 0. Why A can't be 0? Because I mentioned that was relevant for the first step. We also don't want to divide by 0 there. The first of these two inequalities, in other words, this one can be gotten around, worked around if A is 0, by a row interchange as the first step instead, to put the C up in the first upper left corner, in the first row, instead of A. as long as C is non-zero. And then it wouldn't matter whether A is 0 or not. All these steps would still work, and the A would go in place of the C, or the C would go in place of the A, as long as C is non-zero. And we would see C would not be 0, but also still we'd see that AD minus BC should not be 0. If both A and C are 0, then AD minus BC equals 0 anyway. So this condition is not satisfied. Therefore, the only condition we truly need for invertibility is AD minus BC is not 0. And that being true, AD minus BC not being 0 is equivalent to the matrix being invertible. If you know this is not 0, then A will be invertible. You'll be able to find A inverse. And vice versa, if A is invertible, that will mean this is called the determinant. AD minus BC is non-zero. If it is 0, then you'll know A is not invertible. Yeah, this thing's called the determinant. AD minus BC is called the determinant of A, and we write determinant det of A equals AD minus BC. You'll see some textbooks use absolute value notation for determinant. However, that can be confusing because determinants can be negative. Why do people use it? Just because it's a little easier to write when doing certain calculations. It's really best to use DET. And you can think of it in terms of an algorithm. You got your 2 by 2 matrix, multiply the entries on the main diagonal, A times D, and subtract the product of the numbers on the off diagonal or non-main diagonal, B times C. AD minus BC. And that's a helpful way to remember. You should always remember that for the rest of your life. 2 more slides. Is there another way to determine whether a matrix is invertible or not in higher dimensions? Does it generalize to higher dimensions? Yes. But the formula can get very complicated, or even if you think of it as an algorithm, is very complicated and burdensome to compute, even for computers. Once n gets even moderately high, 20, 30, 40, I mean, we're talking 20, 30, 40 instead of 2 million, 3 million, 4 million. The number of computations to determine the determinant grows like n factorial. N times n minus 1 times n minus 2, etc., down to 3 times 2 times 1. And that's something that gets very big very fast. 10 factorial, for example, if I remember correctly, is already over 1 million. I think it's maybe 3 million, something like that. I'm not positive, but 20 factorial, you're getting into scientific notation being used for sure. You don't want to even imagine what a Google factorial is, or a Googleplex factorial, or maybe you do want to imagine it. In 3 dimensions, here's the formula for the determinant. Oh wow, how beautiful. This, which happens to equal that. This is the easier way to remember it. But if you expand all this out, it equals that. What in the world? Where does this come from? Well, it comes from general considerations. I'm not going to go into detail about it. This middle formula in blue is also called the cofactor or Laplace expansion of the determinant across the first row. What in the world does that mean? This thing in blue here. It takes the numbers in the first row, the A, the B, and the C, and multiplies them with appropriately alternating signs, plus, minus, plus, times the determinant of certain 2 by 2 submatrices. If you've never realized this or heard about this before, you may want to pause the video to think about what in the world I'm talking about here. Now, if you're back, I will tell you, notice that EI minus FH is the determinant of this 2 by 2 submatrix. Di minus Fg is the determinant of, well, a broken submatrix, dg in the first column and fi in the second column, di minus Fg. And dh minus Eg is the determinant of another submatrix, this one right here. The first submatrix in red goes with the A, which happens to be in the first column in the first row, whereas this matrix doesn't include numbers in the first column or first row. The second term involving the negative B involves a submatrix not in the same row and column as B. B is in the first row, second column. The submatrix consists of numbers that are neither in the first row nor the second column. And the black one, dh minus Eg, over here, C is in the first row, third column. This submatrix consists of numbers that are neither in the first row nor the third column of the original. There are other cofactor expansions that give the same answer, but I don't want to get into that. Okay? Some people do, some people don't. I think these days more people don't than do. Laplace was a mathematician who lived in the 1700s and did a lot of different math, and he had to do a lot of calculations with determinants, so I think, if I recall correctly, he was the first person to think of determinants. It was just a natural outgrowth of the calculations he was doing. Here are some properties. This is the last slide. These are not the only properties that we're going to talk about. Read my blog, section 1.2, infinity is really big. Visual linear algebra online, section 1.10 is about determinants. And I've got a lot more properties in there. We'll talk about some in lecture 14b. These are going to be the most important ones, though. Determinants have a lot of interesting properties, and they are interesting, that are both useful, both for computation and understanding. These properties work in any dimension, well, most of them do at least. Though I haven't told you how to compute higher dimensional determinants yet, for 4x4 and 5x5 and 6x6 matrices, etc. The most important property is that a square matrix A is invertible if and only if its determinant is non-zero. That applies to any dimensions, including the 3x3 formula that I showed you. That 3x3 matrix will be invertible if and only if that crazy expression is non-zero. So if the expression is zero, then A will not be invertible. Also often helpful is the fact that the determinant of a product A times B is the product of the determinants. Determinant of A times the determinant of B. I'm implicitly assuming A and B are both n by n matrices here or there. Square matrices with the same dimension. Though by writing this, I guess I'm explicitly saying it, but I wanted to say it that way. It also turns out that the determinant of the n by n identity matrix is the number 1. That sounds nice. I mean, in kind of acts like the number 1, right? In times any vector x is the vector x itself, just like 1 times any number is the number itself. In is a multiplicative identity for matrices and vectors, and 1 is a multiplicative identity for numbers. Combining these last two properties means that if A is invertible, you can also say the determinant of A inverse is the reciprocal of the determinant of A, 1 divided by the determinant of A, which will be non-zero if A is invertible. Determinant of A to the -1 power, that really is a power there. And I really can write a division there, because these are numbers, determinants. Okay, so these are, to me, the properties I use the most, because, I mean, some other properties we'll talk about are helpful for computing determinants. And, you know, you can always use technology to compute determinants, though there are limits on how far the technology can go, as I mentioned. So it's really more properties like this that end up being useful when you don't need a computer. That's it. Thanks for watching.